Hello, and welcome to the 7th webinar in our Lunch, Learn, and Dance Wellness webinar series, Mathematics Review. I am Lynn McDonald, Liaison Scientist with the Radiation Safety Institute of Canada. Joining me in our chat room is Maria Costa. Kim Ramos from Arawaku Latin Dance Company in Toronto will lead us in dance beginning at 12:30. Let's take a moment to go over the functionality of the Zoom webinar. The audio and video will be from the presenters only. We have found that although you can access the audio through the computer or telephone, the quality of sound tends to be better when listening from a computer. There is a chat feature where people can discuss. If you would like, take a moment now to say hello and where you're from. If you have questions arriving from the content, please enter them under the Q&A section. As the webinar is only a half hour in length and is immediately followed by our dance session, time may not permit for me to answer them during the webinar. The answers will be posted on our website, along with a link to the video recording and a copy of the slides. This can be found under Education Webinars. I will be sending a confirmation of attendance email after the webinar and will include a link to the page with that communication. I will also include the topics covered and the length of time spent in the webinar, as some people have requested this to send to the professional association. Lastly, I have automatic closed captioning enabled in the slide presentation. If they're being blocked by your Zoom controls, you should be able to adjust so that you'll be able to see them. Rather than a detailed lesson in algebra, this webinar will be discussing concepts which hopefully will make doing the algebra easier. It will be different than the other webinars in the series in that I will be using a document camera for portions to help explain concepts. We'll review the concepts of powers and logarithms and then move on to exponential functions. We'll then talk about the mathematical behavior of radioactive decay when expressed in half-lives and gamma and X-ray shielding attenuation as they are related in half-value layers. From there, we'll show how half-lives and shielding being exponential is expressed mathematically. We will then shift gears and talk about a common probability misconception and how that relates to cancer risk. For those who have struggled with or disliked math in school, needing to learn how to use a new math skill can be intimidating. Even for those who are good at math, needing to revisit a skill that you haven't used for a while can be a challenge. Today's lesson is meant to show some mathematical skills, but more so to explain them conceptually and connect them to practical applications in radiation protection. Educational research shows that connecting learning to prior knowledge helps to develop context and meaning, improving retention and recall. The hope is that by connecting the concepts being overviewed today with concrete applications, it will help the math make more sense. As we only have the half hour together, the material presented will be streamlined to the most relevant points. Nuances will need to be left for more in-depth training. Mathematics, along with other things, provides us with a way to express complicated concepts succinctly, which in turn has led to the advancement of science and engineering. A simple analogy would be to think of mathematics as a language with grammar and rules, which can be used to write down what happens in the world or explain theoretical concepts. The more familiar you are with the rules, the more you can express yourself in the language. Exponents, or more properly called powers, they're a short form of expressing a number being multiplied by itself. The number being multiplied is called the base. The whole expression is called a power. The exponent tells how many times the base is being multiplied by over and over. So for example, I just have to get the right spot. So for example, if you have like 2 to the 3, this is the base and this is the exponent. The whole thing is called a power. And 2 to the 3 tells you that you multiply 2 by itself 3 times. And if you go 2 times 2 times 2, you end up with 8. If you instead had something like 3 to the 5, that tells you to multiply 3 out 5 times. And if you work that out, that ends up being 81. So math has several operations or things you can do to numbers that are inverses. So addition and subtraction are inverse operations. And multiplication and division are inverse operations. So what does that mean for them to be inverses? So let's take a look. So if we have 2 plus 3 equals 5. Once again, math is used to write things succinctly. So we can ask the question, what do you add to 2 to get 5? It's a lot shorter to write 5 minus 2. And you know the answer is 3, because these things are inverse operations. If you have 3 times 4 equals 12, instead of always saying, what do you need to multiply 3 by in order to get 12? The neat way of writing it, or short way, is to use division, that 12 divided by 3 is equal to 4. So an inverse operation is one that undoes the effect of the other, and we have all these symbols to write them really, really shortly instead of big long sentences. In the case of powers, the two questions that can be written so more neatly using an opposite operation are roots and logarithms. So if we go back to the example of 2 times 2 times 2 is equal to 2 to the power of 3, which is 8, you could ask what number multiplied by itself 3 times gives 8. And that is written by taking the cube root. And the answer to that would be 2, because we have to multiply 2 3 times to get 8. But if instead we ask the question, what exponent does 2 need in order to equal 8? Then what we use is logarithms to base 2. And we write that log base 2 of 8. And the question again is, what number do you need to make an exponent if you have the base of 2 in order to get 8? And that answer is 3, because the exponent to get this is 3. So there's really two different opposite operations for powers, and it depends in what way you're looking at it. So just to go through a few more examples. So we have 3 to the 5. We already went through that. That means that it's written out that many times, and the answer is 81. So if we want to ask the question, what exponent do you need for 3 in order to get the answer of 81? That is 5. Now, there's one, if there's no little number subscript down here on your log, the assumption is that it's a 10. So what exponent would you need for a base of 10 in order to get the answer to be 1,000? The answer is going to be 3, because 1,000 is the same as 10 times 10 times 10. So you're multiplying that out 3 times. So that's equal to 10 to the 3. So once again, the answer for a log is telling you what exponent you need if you're using this base in order to get this number. So with that in mind, I'll just let you try quickly. And I know some people, I don't know the background of everyone here. Some people already know this is very basic for them, but for others, it might be a new concept or one they haven't seen since high school. So if you're doing log 5 of 25, you're asking what exponent is it that you would need in order to get 25 if your base is 5. And since 25 is 5 times 5, which is 5 to the power of 2, then the answer here is 2. So why am I talking about powers and roots and logarithms and radiation protection? And the reason why is that physical phenomena like half-lives and shielding attenuation, they can be represented by formulas which use exponents, and they're called exponential functions or exponentials. And logarithms are used when manipulating or solving exponential functions. Exponential functions have the general form. So if you're writing an exponential function, the general form for them is the function has some constant, or that could be out front, and then you have your base, and the power is your variable. So this tells you, your variable tells you how many times to multiply that base out. The base has to be, it can't be negative, it has to be positive, and it has to be, it can't be 0, it wouldn't mean anything. And it's usually greater than or between 0 and less than 1. If it's a 1, then you're just multiplying 1 out a whole pile of times. So functions, they show how one property relates to one or more other properties. One way to visualize a function written as an equation with variables is to graph it. And when we plot a graph in 2 dimensions, if we're drawing that out, the horizontal axis here represents the independent variable. And the one that comes up vertically, that is your dependent variable. So this one basically drives the change in the other. So in radiation protection, time is generally an independent variable, and you plot the time out this way, and it doesn't depend on anything else, so it makes sense that it's an independent variable. Layers of shielding you would put on your horizontal axis as an independent variable, and the amount of intensity getting through or the dose rate and things would depend on the layers of shielding. So we are only going to talk about when time is bigger than 0 and when the layers of shielding is bigger than 0, because that makes sense. So we're only going to be looking at the first quadrant today. So once again, with an exponential function, we usually call that the x-axis or the t-axis. With the exponential function, that independent variable is always up here in the exponent. So equation types, they usually have telltale shapes when they're graphed. So if I'm just going to flip back to the slideshow for a second. So we talk a lot about exponential growth and decay right now with COVID. So this also applies to COVID, but I don't have time to get into that. So exponential growth has this shape of it starting off slowly. It'll start off slowly, and then as the numbers increase, all of a sudden it'll rise up very, very quickly. Exponential decay, on the other hand, starts at some number, and then it'll drop and level out at a certain number. It's not always 0. In this case, it's graphed as 0, but it drops off at a certain number. And if you have the exponent being negative, then you end up with kind of the opposite of what you might expect. So sorry about that. I just skipped along. So with the exponential growth, the base is bigger than 1. And with exponential decay, the base is between 0 and 1. So basically a fraction that's bigger than 0, but not bigger than 1. But with the negative exponents, it flips that around. So both radioactive decay and X-ray and gamma shielding attenuation are examples of this exponential decay. Other types of shielding, like for alpha and beta, they don't follow this. So first I'm going to talk in terms of radioactive decay and half-lives. So this is a little demonstration from a website called PhET, and it's from the University of Colorado, that they have, if you check out PhET, they have tons of science demonstrations. So I'm just going to let it run and talk while it goes. Oops, sorry about that. It didn't start. So you can see over time at the top that it's showing how many decays, and as it approaches the first half-life, which for polonium-211 is around a half a second, that you'll see that the numbers, they have how many polonium and how many lead, that it approaches that halfway point. There's 50 polonium here to begin with, and 0 of the lead. And around the half-life point, it's not exact, but you get to about 50-50. And then when you get to the next half a second passing, you're going to see that there's going to, instead of about 25 have decayed, there's going to be about another 12 have decayed. And that's going to continue on. And why is that? Basically, I made this little video, and this is a common demonstration of half-life decay. If you take something that has a 50-50 chance kind of thing, you could have heads or tails with these, and you drop the pennies on a flat surface, then you have a 50-50 chance of being heads and tails. And I've decided in this demonstration, I'm going to take away all the tails. Those are the ones that have decayed. So they're representing decays. And I threw them all down, and you have 10 heads, 10 tails. But then I noticed that that's an American penny, and that's what their tails look like. So you take away the 11 tails, and those are the ones that decayed. Throw them back down. Next time, again, it's 50-50, but it's not perfect because it's random, right? It's not like, theoretically, you could have all of them be heads or all of them be tails, but you know that it's more likely that it's going to be close to a 50-50 split. So as you keep doing that, the decays happen. Every time there's fewer decays because every time there's fewer of those things left. And that's where you get that exponential decay shape. So we're going to work through a problem and try to keep that idea. Basically, like if you start with 200 grams of something, over time, there's a lot of them, so there's a big drop. But there's fewer and fewer of them as time goes on to be able to decay away, so it doesn't decay as quickly anymore. So we'll flip back to the document camera and work out a few problems. So the formula for exponential decay, just to save time, in terms of half-lives, looks like this. And it's a bit messy looking for those that aren't used to it. But so this NT would represent the amount of isotope remaining at time t. This is the amount of isotope that you had to begin with. E is just a number. It's a little freaky to see that there, but that could be any number, but it's a number and its value is about 2.718. And there's a whole math as to why that is there in this thing here as to why it's done, but I don't have time to get into it. This is called the natural logarithm of 2, and that works out to be a constant that's about 0.693. This is your half-life, and that's the time that has passed. So you have to have your half-life and your time to be in the same units, whether it's years, days, hours, etc., when you're working out these problems. So let's work out the problem where we have a 200-gram sample, like we had in that graph, of technetium-99m. And how much of it's going to be left if 24 hours have passed? Well, the first thing you need to know is what is the half-life of technetium-99m, and the half-life for it is 6 hours. Now, there's two different ways you can work it out. One is if you want to use a formula, and the other one you can just work it out by thinking about what it means. So the first is you write down your formula. And this E, sorry. And then we put in our numbers. We want to know how many are left, or how much is left. We started off with 200 grams. Once again, E is just representing a number, like pi represents a number. Ln 2 is a number, just like pi, like it's just a constant. And then you have your time is 24 hours. So this is in 6 hours, that's an hour, so everything's okay. So how to put that in the calculator? Hopefully this shows up okay. It's easier if you start on the with a calculator like this. You put in the ln 2, you multiply it by 24, divide the whole thing by 6, figure out what that means, change the sign, and then you'll see on the calculators they have these little e to the power of x. So you put that whole thing to the power of x and then multiply that by 200. And that gives you that, because this was in grams to begin with, that the answer is going to come out in grams, and you will have 12.5 grams left. Now, if instead you'd rather just think about what that means, is if you go through and you had 24 hours and the half-life is 6 hours, that means that there was 4 half-lives went by. So that means you start it with 200 grams, and after 1 half-life, you would be down to 100 grams, just like with the pennies, right? We started off with 20 and we went down to 10. And then you have 100 grams, and you'd go down to 50. And that's your second half-life. And then 50 to 25. And then 25 to 12 and a half after your 4 half-lives. So one is you plug in the numbers, whether you understand it or not, as long as you know how to put it in the calculator, you'll get the answer. The other one, you're thinking about it and you're working through it. So hopefully it makes sense. So you may go, well, why would you even use the formula if you don't care for this type? And the main reason why is that this doesn't work well for what if the time that passed was like 15 hours or something like 15 and a half hours. What do you do with that? So what you do with that is you put it in the formula and you convert this to fully hours and it'll work out to exactly how many grams. Whereas using this method, you get a rough estimate for those in-between times. So when we look at that, you can see that formula has a certain shape, that you have a number with a negative and then you have something to the exponent. And when we move over to X-ray and gamma attenuation, there's a number of formulas and you can see, I just wrote out a few of them. So you can see that they all have the same general form. So when you have exposure rate, basically here's the exposure rate with the shield and the exposure rate without the shield. And then there's some other constants and things in the middle. And then X is that variable that you're looking at. That's the thickness of the shielding. If you want to look at beam attenuation, you have the number of photons passing through with the shield in place. You have the number of photons that hit the shield. And then you have some constants up there with the negative. Remember, that's radioactive decay. And then you have the thickness of the shield. You have that variable, again, up in the exponent. So we're going to talk about the third example I have in the X-ray gamma, another way of writing what's going on when you have beam attenuation in terms of intensity. So it looks like a whole lot like when we were talking about the number of photons, basically the intensity with the shield, without the shield. There's something called the linear attenuation coefficient, so how much it decays with distance, and the thickness of the shield. We want to, because we're talking about half-lives and what happens as they cut in half, you cut it in half and a half and a half again, we want to be able to convert this over to half value layer. You can convert this linear attenuation coefficient to half value layer and put that in, and then all of a sudden it works just like the radioactive decay. So if you take a look at this, so after one half value layer, you're at 50%. After two, you're at 25%, 12 and a half, the same type of thing compared to what you started with. So you can see that they behave in similar ways, so you can transfer your knowledge from one to work on the other. There are some rules of thumb that you may see, that 7 half-lives leaves only 1% of the initial activity remaining, and 10 half-lives leave only 0.1%. And if you go back to what we were looking at here, this is why they stopped at 7. Again, it's to show that after 7 half-value layers of shielding, you're down below that 1%. And if we were to go out to the 10th half-value layer, you would also see that you would get to less than 0.1% remaining. One thing to remember is that that's great if you have a reasonable amount of activity to begin with, or a reasonable strength of a beam to begin with. But if you have very strong activity or a very strong beam that you're shielding, you could still have, like 1% could still be a significant amount. So when we take a look at these rules of thumb, where they come from, like after one half-life or one half-value layer, you're going to be at 50%. After two, then you're going to be at 25%, and then 12.5%. And that's where those rules of thumb come from. So quickly, we have about 5 minutes left. I'd like to take a look at some risk-reward misconceptions. So we're completely switching gears here. And I think a lot of people feel that they understand probability well, but if you actually look into it, there's quite a few misconceptions there. Now, some of you may understand this fully, and I don't mean to talk down, but I have run into people that seem to have this misconception. So we just want to take a couple minutes to explain it fully. So some people seem to think that because if you bought a lottery ticket, you could either win or lose, you have a 50-50 chance of winning with each ticket that you buy. And that's not the way that it works. Just making sure I'm on the right screen. So it means that it matters how many different tickets there are, not how many different outcomes there are, right? There's only two outcomes, win or lose, but there's a lot of tickets, different possible tickets. So for Lotto 649, for example, there's one combination at a 13,983,816,000 possibilities. And I missed a comma there. So your chance is 1 out of almost 14 million. So if you buy 2 different tickets, your chance is 2 out of roughly 14 million. So to get a 50-50 chance, which still doesn't mean that you're going to win, you'd have to buy about 7 million tickets. And with cancer risk, if you're exposed to radiation, you could either get cancer or not. The misconception would be that you have a 50-50 chance of getting cancer if you're exposed to radiation, and that's not the case. So the actual risk of cancer due to exposure to radiation is determined by the amount of energy deposited into the tissue over a long period of time, the type of radiation that's interacted with the tissue, and the types of tissue exposed, which is measured in sieverts. All of this is explained in more detail in other webinars. There's an increased risk of 4% for every 1,000 millisieverts of dose, over which, and the natural fatal cancer risk is roughly 25%. By exposing a population of people to 1,000 millisieverts dose over that which a person would experience from a combination of background radiation and for medical purposes, we expect 29% of that population would have a fatal cancer in their lifetime. So this means that if you have 100 people who receive no radiation dose at all, that you would expect that 25 of those people would develop a fatal cancer in their lifetime. And then if you had the lifetime dose, occupational dose you were allowed to get over and above natural background radiation medical exposure, you would expect there was an additional 4 people that you'd have 29 people in that population that would get cancer, a fatal cancer. You can't tell which of these were. It's not a certainty that you're going to get cancer when you're exposed to radiation, and it's not even 50-50. It's based on probabilities. So with that, we wrap up the webinar with letting you know what the Institute is about. So founded in 1980, the Radiation Safety Institute of Canada is an independent, not-for-profit organization offering a variety of informational, consultation, and laboratory services focused on radiation safety. We hope you have enjoyed this mathematics review. Remember, by having strong radiation protection regulations and following safety protocols, we can use radiation safety safely in our workplaces. If you have any further questions about ionizing or non-ionizing radiation, please feel free to contact us at 1-800-263-5803 or email us at info@radiationsafety.ca or visit our website at www.radiationsafety.ca. I just have one last slide with some different resources and references. So the FET at Colorado, Solumaths was used to draw the graphs, and Wolfram Alpha was used to draw some graphs as well. Thank you.